What if I told you that more than 90% of the universe is made up of dark matter and dark energy, forces so mysterious that they shake the very foundations of our understanding? As scientists delve deeper into the cosmos, they continually encounter astonishing celestial bodies and inexplicable phenomena that challenge our perceptions, leaving us in awe of the vast unknown. Prepare to confront the mysteries beyond our reach and ponder the future implications of these findings. Together, we will uncover the intersections where science and technology meet, sparking curiosity about our own place in this grand cosmic tapestry. Stay with us as we navigate these mind-blowing discoveries that could redefine everything we think we know about space. Neutron stars are extraordinary remnants of massive stars that have exploded in supernovae. Their most bizarre characteristic is their density. A typical neutron star packs the mass of about 1.5 suns into a sphere with a radius of roughly 12 kilometers. This means that a sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. Such extreme density challenges our understanding of matter, as it exists in a state where protons and electrons merge to form neutrons, resulting in an incredibly compact and exotic form of matter. Another fascinating feature is the immense gravitational pull of neutron stars. They have such strong gravitational fields that they can warp space-time around them, a phenomenon predicted by Einstein's theory of general relativity. This warping effect can be observed in how light bends around these stars, and can even lead to gravitational waves, ripples in space-time caused by impressive cosmic events. This intersection of neutron stars, gravity, and relativity fascinates scientists and poses questions about the fundamental nature of gravity itself. Neutron stars also exhibit intense magnetic fields that are billions of times stronger than Earth's. These magnetic fields can funnel charged particles into jets that shoot out from their magnetic poles at near light speed. When these jets are aimed towards Earth, they emit powerful beams of radiation, leading to the phenomenon known as pulsars. Pulsars are immensely regular in their rotation and can spin several times per second, acting like cosmic lighthouses. Their predictable signals provide researchers with natural cosmic clocks, allowing us to probe areas of physics that remain unclear. Finally, neutron stars can also collapse into black holes if their mass exceeds a certain threshold. The transition between a neutron star and a black hole continues to puzzle physicists, especially when considering what occurs at this critical boundary. As scientists study these fascinating cosmic objects, they uncover deeper mysteries that challenge the limits of our understanding, making neutron stars one of the most intriguing areas of modern astrophysics. The discovery of black holes has profoundly transformed our understanding of the universe, leading us to reconsider the very fabric of space and time. Initially, black holes were a theoretical concept, born from the equations of Albert Einstein's general theory of relativity. This theory proposed that massive objects can warp the space around them, creating a curvature that affects the passage of time. When black holes were finally confirmed through various astronomical observations, it marked a significant milestone in our understanding of gravity and the nature of reality. Prior to the evidence of black holes, our view of the universe was largely grounded in the idea of the cosmos as a static expanse. Black holes shattered that perception, revealing that the universe is dynamic and full of mysterious regions where the gravitational pull is so intense that nothing, not even light, can escape. This revelation implies that space is not a simple, empty backdrop, but a complex, ever-changing arena. In these gravitational fields, time behaves differently. It can slow down, making the interaction of time with space more intricate than previously imagined. Moreover, The phenomenon of black holes raises intriguing questions about the ultimate fate of matter and energy in the universe. When stars collapse into black holes, they essentially create gateways to realms where our current scientific understanding falters. The possibility that information might be lost in these regions challenges foundational principles in physics, prompting researchers to rethink concepts like causality and the conservation of information, which form crucial pillars of our understanding. As we continue to study black holes through marvels like gravitational wave detectors and powerful telescopes observing the edges of these cosmic enigmas, our perspective on the universe shifts further. We realize that black holes are not just distant phenomena, but keys to unlocking fundamental truths about existence itself. They remind us that while we've made great strides, the universe still holds many secrets waiting to be uncovered, enticing us to explore the intricate tapestry of space and time with new eyes. The discovery of exoplanets with extreme atmospheric conditions has opened a fascinating window into the complexity and diversity of planetary environments beyond our own solar system. These planets often exhibit temperatures and pressures far beyond what we experience on Earth. For instance, some may have scorching temperatures hot enough to melt metals, while others might possess crushing pressures akin to those found deep beneath the ocean. Such extremes challenge our understanding of planetary formation and evolution. The existence of these environments suggests that the processes governing atmospheres are far more intricate than previously thought. For example, we've found exoplanets with thick, cloudy atmospheres composed of exotic compounds like silicate and metal vapors. This has significant implications for our theories about how planetary atmospheres can form and sustain themselves under harsh conditions. By studying these atmospheres, scientists can better understand the physical and chemical processes taking place, enriching our knowledge of atmospheres throughout the universe. Moreover, these extreme conditions provide unique insights into the potential for life elsewhere. While many of these extreme worlds seem inhospitable at first glance, researchers are learning that life might be more adaptable than we assume. The presence of unusual elements and compounds in the atmospheres of these exoplanets could lead to forms of life that are fundamentally different from what we know. This realization underscores the importance of open-mindedness in our search for extraterrestrial life. Finally, the study of these exoplanets challenges us to rethink our place in the cosmos. As we discover planets with conditions that seem beyond imagination, we are reminded of the vast possibilities the universe holds. Each extreme world tells a story of planetary dynamics and resilience, urging us to explore these distant realms further and question what we know about life, chemistry, and the very nature of existence. In recent years, advances in technology and observation techniques have unveiled a fascinating array of celestial objects that are challenging traditional classification systems in astronomy. One significant category is known as rogue planets. These planets do not orbit any star, drifting freely through space instead. Some scientists estimate there may be billions of these planets in our galaxy alone, raising questions about how we define a planet and its relationship to stellar systems. Additionally, astronomers have identified a peculiar object nicknamed Oumuamua, which is believed to be the first interstellar visitor ever detected. Its elongated shape and rapid trajectory defy the common characteristics seen in comets and asteroids. The object displayed unusual acceleration as it traveled through our solar system, suggesting it might be unlike anything we've encountered before. This enigma has inspired new debates about the nature of celestial objects and the very classification systems we have in place. Another compelling discovery is that of exoplanets within unusual environments, particularly those that exist around binary star systems. These planets exhibit unique traits that do not align neatly with classical models, forcing astronomers to rethink what contributes to a planet's climate and potential habitability. The existence of such planets expands our understanding of planetary formation and dynamics, especially in complex stellar systems. Lastly, the discovery of dusty snowballs, comets with an unusual composition, particularly those rich in organic materials, is reshaping our understanding of the building blocks of life in the universe. Their unexpected properties may suggest that the conditions for life might be more widespread than previously thought, adding yet another layer to our understanding of celestial classification. As we continue to explore the cosmos, it seems that our definitions will need to evolve, reflecting the complexity and wonder of the universe we inhabit. Rogue planets, those wandering through the galaxy without a parent star, have profoundly impacted our understanding of planetary formation. These solitary celestial bodies challenge the traditional view that planets must form in orbit around stars. Instead, the presence of rogue planets suggests a more complex and dynamic process, where planets can be ejected from their original systems due to gravitational interactions. Such events shed light on the diverse environments where planets can form and exist. Scientists believe that many rogue planets could have originally formed in a star system before being cast into the dark void of space. This ejection could happen during chaotic events like close encounters with other massive objects. The realization that these planets exist independently is transforming how researchers think about planet formation. It raises fundamental questions. How many more rogue planets might there be? Could they harbor conditions suitable for life, despite their dark and isolated existence? Additionally, the study of rogue planets offers insights into the variety of planetary systems throughout the universe. Many theories revolve around the idea that planets might form in different environments, not solely around stars. This broadens the scope of what we consider when examining the nature and diversity of planetary systems beyond our own. Rogue planets are forcing scientists to rethink their definitions and models of how planets come into being. Moreover, the discovery of these enigmatic wanderers draws attention to the processes that govern the evolution of planetary systems as a whole. As researchers explore their characteristics and distribution, they may uncover new pathways of formation that we have yet to understand fully. With every rogue planet analyzed, our grasp of the cosmos deepens, and the mysteries of planetary formation become increasingly captivating. Fast radio bursts, or FRBs, are incredibly brief yet powerful bursts of radio waves originating from distant galaxies. These phenomena can last just milliseconds, but within that fleeting moment, they unleash as much energy as the sun might emit over several years. The mystery of their origins has sparked the curiosity of scientists and astronomers alike, prompting questions about the nature of the universe itself. The significance of FRBs goes beyond their sheer energy. They serve as cosmic beacons that allow researchers to probe the interstellar medium, the matter that fills the space between stars and galaxies. When an FRB travels through this medium, it interacts with the particles and magnetic fields, leaving behind a unique signature. By studying this signature, scientists can gather valuable insights into the distribution and density of the universe's matter, as well as the characteristics of its evolution over cosmic time. Perhaps one of the most exciting aspects of FRBs is their potential connection to extreme astrophysical events. Some theories propose that they could be linked to neutron stars, particularly those that are rapidly spinning, or to exotic phenomena like the collapse of massive stars. Each new discovery about FRBs pushes the boundaries of our understanding, inviting speculation about the types of cosmic events that can generate such energetic emissions. As we continue to explore these mysterious signals from the cosmos, fast radio bursts are proving to be a key to unlocking deeper questions about the universe. They challenge us to rethink what we know about cosmic phenomena, while offering a glimpse into the intricate and dynamic tapestry of the universe, reminding us that there is still so much left to discover. Dark matter is one of the most intriguing mysteries in cosmology. Comprising about 27% of the universe, it does not emit, absorb, or reflect light, making it invisible to traditional telescopes and scientific measurements. Yet, its presence is inferred through its gravitational effects on visible matter. Galaxies spin at such speeds that, without the additional gravitational pull of dark matter, they would disintegrate. As a result, dark matter plays a crucial role in shaping the structure of the universe. Understanding dark matter helps us piece together the cosmic puzzle. The distribution of dark matter is essential for galaxy formation. In the early universe, tiny fluctuations in density helped dark matter clump together, forming the scaffolding upon which galaxies and large-scale structures would emerge. By studying how these structures evolved over billions of years, scientists gain insights into the universe's history and its expansion. Moreover, dark matter has significant implications for our comprehension of cosmic evolution. It influences the cosmic web, a vast network of galaxies interconnected by filaments formed from dark matter. The behavior of galaxies within this web, including their collisions and mergers, provides vital clues about the dynamics of the universe. This interplay between dark matter and visible matter is crucial for understanding phenomena like galaxy clusters, which are among the largest structures in the universe. Finally, the ongoing search for dark matter continues to inspire advancements in astrophysics. As scientists refine their models and test hypotheses through experiments and observations, they hope to unlock the secrets of this elusive substance. Dark matter's impact on our universe prompts questions about the fundamental nature of reality, pushing the boundaries of what we know and driving our quest for knowledge further into the cosmos. The latest theories surrounding dark energy delve into one of the most profound mysteries of our cosmos: the accelerated expansion of the universe. Observations made in the late 90s revealed that galaxies are not just moving away from each other as might be expected, but are doing so at an increasingly rapid rate. This unexpected acceleration hinted at the presence of a force counteracting the pull of gravity. This force is what we call dark energy, which is thought to make up about 70% of the universe. Current theories propose several models to explain dark energy. One intriguing concept is the cosmological constant, introduced by Albert Einstein over a century ago. This constant suggests that dark energy is a fixed energy density permeating space, remaining static even as the universe expands. While it aligns well with current observations, researchers are exploring whether dark energy is truly constant or varies with the universe's expansion, a scenario known as quintessence. This evolving energy field could change in strength over cosmic time, potentially influencing the fate of the universe in ways we have yet to fully understand. Another significant theory is based on modifications to our understanding of gravity itself. Some scientists propose that the laws of gravity may be different on cosmological scales than on galactic ones. This theory, often referred to as modified gravity, might eliminate the need for dark energy altogether by accounting for the observed acceleration through alterations in the dynamics of space and time at vast distances. This line of inquiry not only challenges existing assumptions, but also encourages a re-evaluation of general relativity in the context of our expanding universe. As research continues, the quest to unravel the nature of dark energy remains at the forefront of cosmological studies, with astronomers and physicists developing advanced telescopes and experiments to gather more data. These efforts aim to refine our models, better understand the universe's expansion, and ultimately reveal whether dark energy is a fundamental property of space, a dynamic force, or a sign that our grasp of gravity is incomplete. Understanding dark energy may hold the key not just to the future of our universe, but to uncovering deeper truths about the fundamental nature of reality itself. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They originate from various sources, including supernovae, black holes, and even distant galaxies. When these cosmic rays interact with the Earth's atmosphere, they can produce secondary particles that researchers can detect. By studying these high-energy particles, scientists gather crucial information about extreme cosmic events and the conditions of space. But there is more to cosmic rays than meets the eye. They may hold clues about the existence of extraterrestrial life. One of the most fascinating aspects of cosmic rays is their ability to reveal the conditions found on other celestial bodies. When cosmic rays collide with surfaces in space, they can create a variety of secondary effects, including chemical reactions and radiation patterns. By analyzing these interactions, scientists can infer the composition of planets and moons, including those within our own solar system, and even those in far-off star systems. Specific patterns or emissions could indicate whether environments exist that could support life or harbor organic building blocks. Moreover, some cosmic rays are thought to be produced or influenced by exotic phenomena that might suggest biological activity, or at the very least, tell us about the processes present in alien worlds. For example, high-energy cosmic rays can generate radiation signatures that may be recognizable in regions with potential microbial life. If, for instance, we find a significant quantity of certain isotopes that tend to be associated with biological processes, it could hint at the presence of life in environments beyond our planet. The study of cosmic rays isn't just about understanding the phenomena themselves. It is also a window into the ongoing quest to answer one of humanity's most profound questions. Are we alone in the universe? With each discovery, we draw closer to expanding our understanding of life beyond Earth, turning the enigmas of the cosmos into potential stepping stones toward finding extraterrestrial existence. The pursuit to decode the mysteries locked within cosmic rays continues to spark not only scientific inquiry, but also our imagination about the possibilities of life among the stars. The discovery of phantom galaxies is a significant development in our understanding of the universe. These galaxies, which seem to exist without the dark matter we associate with traditional galaxy formation, challenge our long-held beliefs. They appear to defy the laws of gravity as we know them, suggesting that there may be more to the cosmos than meets the eye. This revelation raises questions about the basic principles of galaxy formation and the role dark matter plays in it. Traditionally, we have relied on the concept that dark matter acts as a scaffolding, allowing galaxies to form and hold themselves together. The existence of phantom galaxies indicates that some galaxies might form under different conditions or frameworks than those we understand. This pushes astronomers to re-evaluate models of how galaxies can exist, suggesting there may be other, perhaps unknown factors at play. It opens up the enchanting possibility that there are various pathways through which galaxies can evolve. Moreover, these findings ignite curiosity about the nature of the universe itself. If there are galaxies that operate without dark matter's influence, then what does that imply about our cosmic neighborhood? It suggests a more complex tapestry of galaxy formation that could lead to new phenomena yet to be understood. This knowledge might reshape current astrophysical theories and lead to new discoveries about the balance of forces in the universe. Ultimately, the implications of phantom galaxies encourage a more nuanced view of the cosmos. They compel scientists to delve deeper into the mysteries of matter and gravity, pushing us to expand our understanding of how galaxies form and evolve. Each question these phantom galaxies pose serves as an invitation to explore the unknown, reminding us that the universe is far richer and more mysterious than we might have imagined. Galileo Galilei in 1610 are four of Jupiter's most significant natural satellites: Io, Europa, Ganymede, and Callisto. This discovery was monumental, not just for astronomy, but for our understanding of the cosmos. It marked the first time that celestial bodies were observed orbiting a planet other than Earth, challenging the long-held geocentric view of the universe, which posited that everything revolved around our planet. This shift was profound, laying the groundwork for the acceptance of the heliocentric model that places the Sun at the center of our solar system. Each of these moons has unique characteristics that continue to amaze scientists and spark curiosity. Io is the most volcanically active body in the solar system, hosting hundreds of volcanoes, some of which erupt with lava fountains that reach towering heights. Europa, on the other hand, is covered in a thick layer of ice, believed to harbor a vast ocean beneath its surface. This makes it one of the prime candidates in the search for extraterrestrial life. Ganymede, the largest moon in the solar system, not only has a magnetic field, but also shows signs of geological activity. Lastly, Callisto is heavily cratered, indicating a long history of impacts. The discovery of the Galilean moons challenged scientists to rethink what planetary systems could look like. It suggested that moons could be as diverse and complex as planets themselves, leading to an understanding that satellites might play critical roles in the dynamics of their respective systems. This realization prompted astronomers to search for similar multi-moon systems around other planets, reshaping our exploration of exoplanets and their moons. Today, as we continue to discover new planetary systems beyond our own, the Galilean moons serve as a fundamental reference point for understanding these distant worlds. They remind us that the universe is full of wonders, and by studying our own celestial neighbors, we gain insight into the possibilities of life and the mechanics of other star systems. The lessons learned from these remarkable moons encourage us to ask more questions and explore further, deepening our journey into the vast cosmos. The discovery of gravitational waves has opened an extraordinary new chapter in the field of astrophysics. These ripples in the fabric of space-time, first detected in September of 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, are generated by some of the universe's most violent and energetic events, like the collision of black holes or neutron stars. Prior to this discovery, our understanding of the cosmos was primarily based on electromagnetic waves, light and radio waves we could observe with telescopes. Gravitational waves provide a completely new way of observing and understanding the universe. One of the most significant aspects of gravitational waves is their ability to travel unimpeded through matter. Unlike light, which can be blocked or absorbed, these waves carry with them crucial information about their origins. When we detect gravitational waves, we gain insights into events that might not be visible through traditional means. For instance, while light from merging black holes may be too faint or completely obscured by dust, the gravitational waves produced during the event can reveal details about the masses and behaviors of these objects. This has effectively expanded the toolkit of astronomers and physicists. Moreover, this groundbreaking discovery has allowed scientists to engage in what is known as multi-messenger astronomy. For the first time, astronomers can combine data from gravitational waves, light, and other cosmic signals to create a more comprehensive understanding of cataclysmic events. For example, the detection of gravitational waves from a neutron star merger was simultaneously observed across the electromagnetic spectrum, including gamma rays and optical light. This cross-collaboration enhances our grasp of the processes involved in these cosmic occurrences and highlights the interconnectedness of different aspects of the universe. Gravitational waves have revolutionized our approach to cosmic events by providing a novel way to observe the universe. They offer insights into previously hidden processes, enabling collaborative studies that blend different forms of cosmic data. As we continue to refine our detection methods and increase the sensitivity of instruments, who knows what other astonishing discoveries await us in the depths of space-time. The journey into understanding the universe has only just begun, thanks to this incredible expansion of our observational capabilities. Recent discoveries surrounding colliding galaxies have opened a fascinating new chapter in our understanding of how galaxies form and evolve. When two galaxies collide, it's not merely a chaotic event, it's a cosmic dance that has profound implications for their structure and future. These collisions can trigger explosive bursts of star formation, known as starbursts, as the gravitational interactions compress gas and dust in the galaxies. This process leads to the creation of thousands of new stars over a relatively short time, reshaping the galactic environment and dynamics. Furthermore, these collisions provide a unique opportunity to study the role of dark matter in galaxies. Observing how colliding galaxies behave helps scientists map the distribution of dark matter, which makes up a significant portion of the universe's mass, yet remains invisible. When galaxies merge, their dark matter halos, vast regions surrounding galaxies, interact and can be observed indirectly. Insights gleaned from these interactions enhance our understanding of dark matter's influence on galaxy formation and stability. Moreover, the morphology of the resulting galactic structures can reveal clues about their histories. When we look at merging galaxies, we often find new features, such as tidal tails or loops formed from the gravitational pull. These structures show not only how the galaxies interacted, but also provide evidence of their past. Understanding these formations allows astronomers to piece together the evolutionary timeline of galaxies, illustrating how they grow and change over billions of years. Finally, the aftermath of such collisions raises intriguing questions about the fate of galaxies in the universe. As galaxies merge, they may eventually form a larger galaxy, resulting in a more complex and diverse structure. This process highlights the idea that the universe is not static. Rather, it is continually evolving, with galaxies shaped by their interactions with one another. These discoveries remind us that every star and galaxy we see today carries within it the story of its past encounters, a testament to the dynamic and interconnected nature of the cosmos. The cosmic microwave background radiation, a remnant from the Big Bang, has been a treasure trove for researchers seeking to understand the early universe. One of the most surprising findings has been the uniformity of this radiation. Across vast distances in space, the temperature variations are incredibly slight. This uniformity suggests that the early universe was smooth and homogeneous, leading to the development of cosmic structures as we know them today. However, alongside this smoothness, researchers have detected intriguing anomalies, such as the so-called cold spot. This region appears cooler than expected and has led to speculation about potential explanations, ranging from large-scale cosmic structures to perhaps even a multi-universe scenario. The existence of these cold and hot patches raises questions about the initial conditions of the universe and whether they align with our current models of cosmic evolution. Moreover, advanced studies of polarization within the cosmic microwave background have shed light on phenomena such as gravitational waves. These ripples in the fabric of space-time are believed to have been generated during the inflationary phase of the early universe. Detecting these polarization patterns gives us crucial hints about the violent events that shaped our cosmos just moments after the Big Bang, enhancing our understanding of the universe's infancy. As researchers continue to pass through the data, each discovery hints at deeper layers of complexity in our universe. The cosmic microwave background is not merely a relic, it is a window into our universe's past, holding clues about its formation, structure, and potentially even its fate. Each revelation not only answers age-old questions, but often opens the door to new mysteries, urging us to look closer and ponder the vastness of existence itself. Surveys of ultra-diffuse galaxies have significantly reshaped our understanding of galaxy formation, presenting intriguing challenges to established theories. Unlike typical galaxies, these ultra-diffuse galaxies boast a vast number of stars spread across an expansive area, yet they contain very little visible matter. This peculiar characteristic raises questions about how such galaxies can exist and thrive without the expected amounts of dark matter or gas typically associated with galaxy formation. Traditionally, galaxies are understood to form in a specific way, accumulating mass over time through gravitational attraction and interactions with other galaxies. The emergence of ultra-diffuse galaxies suggests that the processes at play may be more varied and complex than previously thought. Some of these galaxies are found in clusters, leading scientists to hypothesize that interactions within these environments could play a crucial role in their development. These interactions can strip away gas and dark matter, creating a galaxy that is large and star-rich but diffuse. Moreover, the discovery of ultra-diffuse galaxies hints at the possibility of alternative formation mechanisms, such as direct collapse or other processes that do not fit neatly into existing models. Researchers are investigating whether these galaxies represent a distinct branch of galaxy evolution, or if they can be understood through a modified lens of current theories. Their study is ongoing, and early observations reveal a spectrum of conditions surrounding their formation, from different environmental influences to variations in their chemical compositions. The existence of ultra-diffuse galaxies compels astronomers to rethink long-held beliefs about how galaxies develop and evolve. It opens up a world of possibilities, inviting experts to explore new pathways of galaxy formation and the role that dark matter may play in building the cosmos. As we gather more data on these enigmatic structures, we inch closer to a deeper understanding of the universe and its fascinating diversity. The concept of the multiverse theory is truly mind-bending, suggesting that our universe is just one of many, possibly infinite universes existing alongside each other. Recent advancements in cosmology have sparked intriguing discussions about what this means for our own universe. One key study revolves around the idea that these parallel universes may all arise from the same fundamental fabric of reality, governed by the same physical laws, but manifesting unique characteristics. One fascinating aspect of this theory is the implication that different universes can have different values for fundamental constants, which could lead to entirely different forms of life or entirely different physical phenomena. For instance, while our universe supports life as we know it, other universes could experience different laws of physics, leading to various kinds of existence, or none at all. This diversity suggests a rich tapestry of realities where, in some universes, time may not even flow as it does in ours. Additionally, findings related to cosmic inflation support the multiverse theory. Cosmic inflation describes a period just after the Big Bang when the universe expanded exponentially. Some scientists propose that this inflation could create bubbles of space-time, each one potentially evolving into its own universe. Discovering evidence of these bubbles or variations in the cosmic background, radiation could lend credence to the idea that our universe is merely one bubble in a vast multiverse. Ultimately, the discussions surrounding the multiverse challenge our understanding of existence itself. As scientists investigate deeper into the nature of reality, we may begin to question not just the mechanics of our universe, but our very place in the grand cosmos. With each discovery, we inch closer to unraveling the mysteries of the universe, and perhaps the incredibly perplexing notion that we are part of something far more expansive than we have ever imagined. The idea of time travel through wormholes offers a fascinating perspective on our understanding of time and space. To envision this, imagine the universe as a vast piece of fabric where space and time are intertwined. Wormholes are theoretical shortcuts through this fabric, connecting two distant points in both space and time. If such structures exist, they could allow for travel not only across great distances, but also to different times, challenging our traditional concepts of linear progression. At the heart of this concept lies the peculiar nature of wormholes. They are formed by the curvature of space-time, stemming from Einstein's theory of relativity. Simply put, relativity tells us that massive objects like stars and planets warp the space around them, and a wormhole is an extreme expression of this warping, bringing two separate points together. This defies our everyday experience where time seems to flow steadily forward, offering instead the tantalizing possibility of moving backward or skipping forward in time. However, the idea of using wormholes for time travel is riddled with complications. For one, they are purely theoretical and have yet to be observed. Additionally, even if they could exist, they would require exotic matter with negative energy to remain stable, something we have not yet been able to create or find. This leads to questions about causality, or the cause and effect relationship that governs our understanding of events. Time travel could potentially open a Pandora's box where actions in the past alter the present in unexpected ways. Lastly, these notions compel us to rethink fundamental concepts. If time travel were possible, our views on history, fate, and the universe would shift. Time would no longer be a one-way street, but rather a more complex landscape with multiple paths and realities. Embracing the idea of wormholes invites us to ponder not just the how, but the profound philosophical implications of existing in a universe where time might be more fluid than we can currently comprehend. The concept of parallel universes has captivated the imagination of scientists and philosophers alike, prompting intriguing questions about the nature of reality. Notable breakthroughs in this field stem largely from advances in theoretical physics. Researchers have explored ideas within quantum mechanics, string theory, and the cosmic multiverse, each offering distinct perspectives on how multiple universes could exist simultaneously alongside our own. One significant breakthrough comes from the field of quantum mechanics, particularly the interpretation known as the many worlds interpretation. This suggests that every possible outcome of a quantum event occurs in its own parallel universe. For instance, if you flip a coin, instead of merely landing on heads or tails, there exists a universe where it lands on both. This interpretation implies a vast multitude of realities branching out from each decision made. It challenges our understanding of choice, suggesting that every action spawns a new reality, forever expanding the dimensions of existence. In addition to quantum mechanics, string theory presents another layer to the discussion of parallel universes. This theoretical framework posits that fundamental particles are not points but rather tiny vibrating strings. In this model, the universe could contain multiple dimensions beyond our perceivable three. Some scientists theorize that these additional dimensions could harbor entirely different universes, each governed by varying physical laws. This opens up the possibility of alternative civilizations and environments, dramatically altering our perception of what is conceivable. These discoveries reshape our understanding of reality itself, making it a far more complex and interconnected tapestry. The implications of parallel universes not only challenge our perceptions of science, but also invite profound philosophical questions. Are we simply one of many versions of ourselves dispersed across an infinite multiverse? As research continues, each revelation adds depth to our comprehension of existence, further blurring the lines between science fiction and science fact. The journey into understanding parallel universes is ongoing, and who knows what insights the future may hold. Quantum entanglement is one of the most intriguing aspects of quantum mechanics, and it presents a fascinating challenge to our conventional understanding of locality, especially when we observe its effects on cosmic scales. Traditionally, locality in physics suggests that objects can only influence one another through direct interaction at nearby distances. In other words, something that happens in one place should not instantly affect something happening far away. However, entangled particles seem to defy this idea. When two particles become entangled, they exist in a shared state regardless of the distance separating them. This means that if something is done to one particle, the other particle will instantaneously respond, no matter how far apart they are, whether they are a few meters away or light years apart. This instantaneous connection doesn't rely on any force traveling through space, which raises profound questions about the nature of information, influence, and the very structure of the universe itself. This phenomenon has been observed in various experiments, some involving particles over significant distances. These cosmic scale experiments push the boundaries of our understanding and suggest that the universe is much more interconnected than we can perceive. It opens the door to new ideas about how information might be transmitted across vast distances, challenging the classical idea that nothing can travel faster than light. The implications of quantum entanglement stretch beyond mere curiosity. They could reshape our fundamental principles of physics. If locality is not as strict as once thought, it might lead us to rethink our entire framework of space and time. In a universe where entangled particles can instantaneously affect one another, it invites us to consider a more holistic view of reality, where everything could be more intertwined than we ever imagined. Time dilation is a fascinating phenomenon that emerges from Einstein's theory of relativity, illustrating how time can flow at different rates depending on the strength of a gravitational field. In extreme gravitational environments, such as near black holes, time slows down relative to regions of weaker gravity. This unexpected behavior leads us to several profound implications for our understanding of the universe. One of the most significant implications is how we perceive the passage of time in different parts of space. For instance, an observer close to a black hole would experience time much more slowly than someone far away from it. This means that while only a few minutes may pass for someone near the black hole, for others observing from a distance, hours or even years could elapse. This phenomenon challenges our intuitive grasp of time and raises questions about the nature of reality itself. Furthermore, the consequences of time dilation affect our exploration of the universe. It complicates deep space missions, as astronauts traveling at high velocities or near massive objects could return to find significant discrepancies in their ages compared to those who remained on Earth. It nudges us to rethink our notions of aging and lifespans in a cosmic context, making us realize that time is not a universal constant, but rather a malleable entity. Finally, the implications of time dilation resonate with the grander structure of the cosmos, shedding light on the behavior of galaxies and the expansion of the universe. Understanding how time unfolds in varying gravitational fields allows astronomers to better interpret distant astronomical events and their implications for cosmic evolution. As we delve deeper into these mysterious realms, we continue to uncover layers of reality that challenge traditional narratives and expand our grasp of the universe. Motivated scientists and stargazers alike, offering surprising insights into the nature of these distant worlds. Enceladus, one of Saturn's smallest moons, surprises researchers with its plumes of water vapor and ice particles that shoot into space from cracks in its icy surface. This discovery has led to the intriguing possibility of a subsurface ocean beneath the thick ice, creating a benign environment that could potentially harbor life. What truly astonished scientists was the composition of the geyser eruptions. Observations from the Cassini spacecraft revealed that the ice plumes contain salts and organic molecules, suggesting that there are interactions occurring between the ocean and the moon's rocky core. This finding raises fascinating questions about the chemistry that could support life in these extreme conditions. It seems that Enceladus is not just a relic frozen in time, it harbors a dynamic interior that fosters a rich environment for life. Similarly, Europa, one of Jupiter's largest moons, showcases intriguing features that hint at a watery world beneath its icy crust. The strong evidence of a vast ocean beneath Europa's frozen surface, combined with the detection of surface features that could indicate geysers or cryovolcanic activity, suggests that the moon is geologically active. The potential for plumes similar to those observed on Enceladus adds to the excitement surrounding Europa as a prime candidate in the search for extraterrestrial life. These discoveries challenge our understanding of where and how life might exist beyond Earth. The ongoing exploration of these icy moons reveals that our solar system is far more dynamic and complex than we ever imagined. Ice geysers, with their vast implications and startling revelations, remind us that even in the coldest corners of space, the ingredients for life could very well be present, beckoning us to explore further. The surface of Venus presents a formidable environment that challenges our traditional ideas about habitability in the universe. Once considered a potential sister planet to Earth, Venus has revealed itself to be a hostile world. Its atmosphere is thick with carbon dioxide, creating a crushing pressure more than 90 times that of Earth's surface. This oppressive atmosphere traps heat, leading to surface temperatures that soar to around 430 degrees Celsius, boiling any lead into a liquid. These extreme conditions force scientists to reconsider what we mean by habitability. Conventional wisdom suggested that life could thrive on planets with moderate temperatures and water, key ingredients for life as we know it. However, if a planet like Venus, which is similar in size and proximity to the Sun, can develop such inhospitable conditions, it raises crucial questions about the nature of life itself. Could life survive in environments vastly different from our own, perhaps finding a way to adapt to features like intense pressures, high temperatures, or corrosive atmospheres? Exploring these concepts invites us to consider a wider array of possibilities for life beyond Earth. Microbial life has been found thriving in extreme environments on our own planet, such as hot springs and deep ocean vents, indicating that life may not require the conditions we typically associate with livable worlds. The study of Venus stresses that we may have to expand our criteria for what constitutes a habitable environment. Ultimately, the findings on Venus underscore the complexity of planetary evolution and climate dynamics. This presents a cosmic perspective that reminds us of the diverse conditions that could potentially support life elsewhere in the universe. As we probe deeper into these questions, we embark on a journey that shifts our understanding of life and its many possible forms across the cosmos. In recent years, Mars has revealed a treasure trove of geological features that challenge our understanding of its past. Once thought to be a cold, barren landscape, extensive observations have uncovered signs that suggest a much more dynamic history. For instance, research teams have identified gigantic channel systems and ancient riverbeds, hinting at the existence of flowing water on the surface long after the formation of the planet. These formations tell us that Mars may have once been a planet teeming with a watery environment, potentially supporting life. One particularly compelling discovery involves the presence of vast plains covered in what appear to be ancient ice deposits. These plains, known as the northern plains of Mars, host intricate features resembling those formed by glaciers on Earth, suggesting that the planet experienced significant glacial activity. Such findings propose that not only did Mars have liquid water in the past, but it also underwent ice ages and climatic changes that could have radically altered its surface. Current models of Martian geology indicate a complex interplay between warming and cooling periods, pointing toward a much more nuanced climate history. Moreover, magnificent volcanic structures like Olympus Mons, the tallest volcano in the solar system, speak to a time when volcanic activity was far more vigorous than previously believed. These vast shields, towering mountains, and fissures extend hundreds of kilometers, offering evidence that the planet was geologically active for a far longer period than scientists had assumed. In addition, the presence of tectonic features, including rift valleys and faults, suggests that Mars experienced considerable internal stresses, similar to tectonic activity on Earth. These astonishing geological features invite us to consider the possibility that Mars was not merely a static world, but one shaped by complex processes over millions of years. Each new discovery hints at a vibrant past that challenges our assumptions and fuels our curiosity about what Mars could have been and whether it might still harbor some form of life beneath its harsh exterior. More importantly, as we continue to explore Mars, we uncover the remnants of a planet that, in many ways, explores the very conditions that could lead to the emergence of life itself. Saturn's rings are among the most stunning features in our solar system, consisting of countless particles that range from tiny ice grains to massive chunks of ice and rock. Their intricate structure, including bright and dark bands, diverse thicknesses, and varying compositions, intrigues scientists and casual observers alike. These rings are not just beautiful, they also raise compelling questions about the longevity and evolution of planetary ring systems throughout the universe. One of the most striking aspects of Saturn's rings is their youth in cosmic terms. Although they appear magnificent today, many scientists believe they may be relatively new, forming just a few 100 million years ago. This prompts an important question: how long can such rings endure? The answer lies in understanding the dynamic processes at work. The forces exerted by Saturn's gravity, the interactions among ring particles and external influences, such as meteoroid impacts or the tidal forces from Saturn's moons, all play a role in shaping the ring's lifespan. Interestingly, Saturn's rings face constant wear and tear. The particles composing the rings are constantly colliding, leading to erosion and even the possible loss of material. Over time, these collisions can cause ring particles to drift into Saturn's atmosphere or coalesce into larger bodies, effectively diminishing the ring system. This erosion process, combined with gravitational influences, suggests that Saturn's rings could last for a mere few 100 million years before they might dissipate entirely, raising fascinating questions about the origin and fate of similar structures around other planets. By comparing Saturn's rings with those of other gas giants, such as Jupiter, Uranus, and Neptune, scientists can further explore the life cycle of ring systems. For instance, some of these planets possess faint, fleeting rings. Understanding the differences sheds light on how unique environments and histories influence their formation and longevity. Ultimately, by studying Saturn's majestic rings, we not only admire their beauty, but gain insight into the processes that govern celestial bodies, inviting us to ponder more deeply the mysteries of our universe. Recent studies of exoplanet interiors have significantly refined our understanding of the environments that might support life beyond Earth. In the excitement of discovering thousands of exoplanets, scientists have turned their gaze toward what lies beneath the surface of these distant worlds. By analyzing their mass, size, and density, researchers are piecing together the compositions and potential geological activity of these bodies. This insight is crucial because a planet's interior can greatly influence its ability to harbor life. Traditionally, we considered planets like Earth as the benchmark for habitability, However, studies show a broader spectrum of potential environments. For example, some exoplanets may be primarily composed of water, while others could possess thick atmospheres rich in gases like hydrogen or helium. These diverse compositions can lead to different surface conditions and geological processes, shaping how climates evolve. Findings suggest that worlds with substantial water and volcanic activity could create the chemical diversity necessary for life, akin to the early Earth. Moreover, advances in telescope technology have enabled scientists to analyze the atmospheres of these exoplanets. The presence of certain gases, such as oxygen and methane, can signal biological processes, yet these studies indicate that even seemingly inhospitable environments might have hidden potential. For instance, planets that experience intense pressure and heat might still host microbial life in subsurface oceans or within their rocky mantles, where conditions are vastly different from the hostile surface. Overall, as we uncover the complexities of exoplanet interiors, our perspective on habitability expands. We begin to understand that life may not be a simple adaptation, but could emerge in unexpected environments. This evolving knowledge paints a broader picture of the universe, spurring our curiosity about the myriad forms life could take beyond our own planet, waiting to be discovered among the stars. Of supernovae have reshaped our understanding of how stars live and die, particularly emphasizing the diversity of these explosive events. Traditionally, models of stellar life cycles suggested that supernovae were primarily the result of massive stars exhausting their nuclear fuel. However, new data reveals a more complex picture, indicating that even stars we once thought were stable or less massive can produce supernovae. This revelation suggests that the processes leading to these cosmic explosions are less straightforward than previously believed. One surprising finding comes from the observation of certain types of supernovae, specifically the type called Type Ia. These explosions are traditionally linked to white dwarfs, which are remnants of stars that have shed their outer layers. It was believed that these white dwarfs could only explode when they reached a certain mass by accumulating material from a companion star. However, recent discoveries show that other mechanisms may trigger these explosions, such as the merging of two white dwarfs. This insight is significant because it expands the criteria under which supernova can occur and can change our understanding of stellar evolution. Moreover, observations from advanced telescopes have unveiled a wealth of diversity among different supernova types. Some supernovae are more energetic and last longer than models would predict, while others seem to dim unusually quickly. These variations hint at a rich tapestry of stellar behavior that our current theories don't fully encompass. The implications are profound, suggesting that the life cycles of stars are influenced by a range of factors that may include their environment, rotation rates, and chemical compositions. As astronomers continue to gather data, especially from powerful observatories, the landscape of our understanding continues to evolve. Each new discovery not only refines our knowledge of supernova triggers, but also contributes significantly to our grasp of the universe's history and the formation of elements. The journey to unravel these cosmic events not only inspires awe, but also highlights the beauty and mystery of the cosmos, emphasizing how much more we have yet to learn about the life cycles of stars. The detection of an electromagnetic counterpart to gravitational waves from a neutron-star merger marked a monumental moment in modern astrophysics. This event, known as GW 170817, not only confirmed theories about the origins of heavy elements, but it also opened up a new era for multi-messenger astronomy, where different types of signals are combined to deepen our understanding of cosmic phenomena. When two neutron stars collide, they create ripples in space-time, emitting gravitational waves that can be detected on Earth. Following the gravitational wave detection, astronomers identified the electromagnetic counterpart, a burst of light known as a kilonova. This sudden wave of light was much brighter than typical novas and revealed itself across the electromagnetic spectrum, from gamma rays to optical light. The brilliance of this burst provided strong evidence that neutron star mergers are indeed responsible for the creation of heavy elements like gold and platinum. Within hours of the gravitational waves being detected, telescopes across the globe turned their attention to the location in the sky where the event was observed. The joint observations revealed not only the kilonova explosion, but also the afterglow, which persisted and evolved over time. This collaboration offered a wealth of data, showing how neutron star mergers uniquely contribute to the elemental makeup of the universe and revealing insights about the conditions during and after such cosmic collisions. Furthermore, the success of this multi-messenger approach excited scientists about future astronomical endeavors. It demonstrated that observing gravitational waves in conjunction with electromagnetic signals could unlock secrets about the universe's most violent events. The insights gleaned from this neutron star merger have paved the way for a deeper understanding of the life cycles of stars, the formation of elements, and the very fabric of our universe. Gamma-ray bursts, or GRBs, are among the most powerful explosions in the universe, releasing immense amounts of energy in the form of gamma rays. These bursts can outshine entire galaxies for brief moments, and they signify significant cosmic events, typically the collapse of massive stars or the merger of neutron stars. By studying the characteristics of gamma-ray bursts, scientists gain critical insights into phenomena that indicate powerful processes taking place in the universe, leading to our understanding of cosmic evolution. The intense light emitted by gamma-ray bursts allows astronomers to study them across vast distances. Observations of these bursts have revealed that they can vary in duration, spanning from a few milliseconds to several minutes. The shorter bursts, often associated with the deaths of massive stars, indicate rapid events, while longer bursts, typically linked to neutron star mergers, suggest more prolonged processes. This variation in duration helps scientists categorize the types of GRBs and understand the underlying mechanisms that produce their extraordinary energy. Moreover, gamma-ray bursts serve as beacons that illuminate the surrounding universe. The afterglow of a burst provides valuable data, not only about the characteristics of the explosion itself, but also about the environment in which it occurred. By analyzing the light that comes after the initial explosion, researchers can deduce the composition and structure of distant galaxies, providing glimpses into their formation and evolution. Essentially, these cosmic fireworks enable astronomers to probe the early universe and its development. Gamma-ray bursts are not just remarkable phenomena, they are crucial to unraveling the mysteries of the universe. As scientists continue to observe and analyze these events, they deepen our understanding of the most energetic processes in existence, offering insights that connect the distant past of the universe with the present day. Each burst is like a flash of light in the darkness, revealing the vast complexity and dynamism of the cosmos. The study of cosmic inflation has revealed some truly astonishing insights that challenge and deepen our understanding of the Big Bang. Initially proposed in the early 1980s, inflation suggests that a split second after the Big Bang, the universe expanded at an exponential rate. This rapid growth resolved several enigmas that troubled scientists, like the uniformity of the cosmic microwave background radiation. Before inflation theory, explaining how distant regions of the universe could have similar temperatures and densities seemed almost impossible. One of the most shocking revelations is that inflation paints a picture of a far more complex early universe than we had imagined. Rather than a smooth expansion, inflation implies that the universe might have undergone rapid fluctuations, leading to regions of varying densities. These tiny quantum fluctuations evolved into the vast structures we observe today, such as galaxies and clusters of galaxies. This transformation from the quantum realm to the cosmic tapestry underscores that the seeds of our universe's structure were laid down during this incredibly brief moment of monumental inflation. Furthermore, the concept of inflation introduces the idea that our universe may not be unique. In fact, some theories suggest that inflation could occur repeatedly, giving rise to a multiverse scenario. Each bubble within this multiverse could evolve into its own distinct universe, potentially with different physical laws or constants. This proposition pushes the boundaries of our comprehension, raising profound questions about reality and our place in the cosmos. Ultimately, cosmic inflation doesn't just enhance the Big Bang theory, it transforms it. It leads us to consider not only how our universe began, but also opens the door to understanding what might lie beyond it. Each revelation from inflation carries implications that are as exhilarating as they are humbling, reminding us that the quest to grasp the cosmos is an ever-expanding horizon, full of mysteries waiting to be uncovered. Cosmic voids, those vast expanses of space that contain very few galaxies, have recently emerged as important players in our understanding of the universe's composition. Traditionally, astronomers viewed these voids as mere empty spaces between galaxies. However, recent studies have shown that they are not just nothing. Instead, they provide a unique insight into the overall distribution of matter, the influence of dark energy, and the structure of the universe as a whole. Scientists have discovered that the characteristics of cosmic voids can help us understand the effects of dark energy on the cosmos. Dark energy is the mysterious force driving the accelerated expansion of the universe, and it makes up about 70% of the total energy content of the universe. By analyzing the size and density of these voids, researchers can gauge how this dark energy interacts with matter. These investigations have revealed that voids are often larger and more elongated than previously expected, reshaping our understanding of the very fabric of space. Additionally, the latest studies suggest that cosmic voids can influence the formation and evolution of galaxies. Galaxies tend to form along the edges of these voids due to the gravitational effects of the surrounding matter, leading to interesting patterns observed in galaxy distributions. By studying the contours of these voids, scientists have gained valuable insights into how galaxies were formed and how the universe evolved over billions of years. As we redefine our perception of these vast cosmic expanses, it's becoming clear that they are a fundamental component of the universe's makeup. Each void provides clues about cosmic history and the interplay between dark matter and dark energy, painting a more complex picture of a universe that is ever-evolving and far more dynamic than we once believed. These studies of cosmic voids are not just filling in the blanks, they are revolutionizing our understanding of the universe itself. Cosmos. We observe distant galaxies racing away from us, their light shifting toward redder wavelengths. This phenomenon, known as redshift, is a clear indication that the universe is expanding. However, the unexpected speeds at which these galaxies are moving raise intriguing questions. The conventional understanding, based on gravity and dark matter, does not completely account for the observed motions, leading scientists to wonder if unknown forces might be at play. One of the most fascinating aspects of these anomalies is their connection to the notion of dark energy. While we perceive most of the universe's mass through familiar means, such as stars and planets, a substantial portion remains elusive. Dark energy is hypothesized to comprise about 70% of the universe, acting as a driving force behind its accelerated expansion. This mysterious repulsive force could explain why we observe galaxies moving away from one another more quickly than expected. Additionally, Researchers have detected variations in the velocities of clusters of galaxies that hint at gravitational interactions not fully understood. These observations suggest that there may be additional unidentified forms of matter or energy influencing galactic motion. If confirmed, this could revolutionize our understanding of the cosmos and the fundamental laws that govern it. In the quest to decipher these anomalies, scientists continue to gather data from advanced telescopes and surveys. Each discovery adds a piece to the puzzle, enhancing our comprehension of the universe's makeup. The quest for knowledge drives researchers to explore these unknown forces, reminding us that even in our most advanced explorations, the universe still holds many secrets waiting to be unraveled. Pulsars, those incredibly dense remnants of supernova explosions, exhibit some truly fascinating characteristics that can hint at the existence of exotic matter. These highly magnetized, rotating neutron stars emit beams of radiation from their magnetic poles, but it's their very nature and behavior that capture the imagination of scientists. One of the most striking features of pulsars is their rotation. Some can spin at astonishing speeds, with certain pulsars completing a rotation in just a fraction of a second. This rapid rotation raises important questions about the forces and materials at play in these extraordinary objects. The density of pulsars is another characteristic that sparks interest. A typical pulsar can contain more mass than the Sun, all packed into a sphere only about the size of a city. This extreme density suggests the presence of matter that behaves differently than what we encounter on Earth. Many physicists suspect that the core of pulsars might harbor exotic forms of matter, such as quark matter, which is theorized to exist when neutrons break down into their fundamental components, quarks. Such conditions remind us that the universe often operates on principles that challenge our everyday experiences and understanding. Additionally, unusual phenomena like glitches in pulsar rotation give further insight. These sudden changes in spin rate suggest that something is causing turbulence within the neutron star. They could be caused by interactions with this exotic matter, potentially reshaping our understanding of how pulsars work. Such glitches prompt scientists to consider theories about how matter behaves under extreme gravitational and density conditions, which are otherwise unobservable on our planet. Finally, the magnetic fields of pulsars are another area of intrigue. Some pulsars exhibit magnetic fields much stronger than what we can create in laboratories. This intense magnetism could be influenced by exotic matter within, which might have properties we're still just beginning to comprehend. These collective peculiarities make pulsars not just objects of study, but gateways to exploring the very fabric of matter and the fundamental forces of the universe, hinting tantalizingly at phenomena that could redefine our understanding of the cosmos. The discovery of new asteroid belts in distant solar systems has sparked a fascinating re-evaluation of our existing models of how solar systems form. Traditionally, we viewed solar systems as evolving in a relatively uniform manner, where planets and other celestial bodies emerged in a predictable, structured way. However, these new findings suggest that the processes involved in solar system formation are more complex and variable than we previously understood. Asteroid belts are often remnants of material that did not coalesce into planets. They suggest that there may be a variety of factors, such as gravitational influences from giant planets or the dynamics of gas and dust, that can affect how these materials behave in evolving solar systems. The presence of multiple asteroid belts in a single system indicates that there might be different pathways to forming planetary systems. These pathways might be influenced by different conditions and events, producing unique outcomes in each solar system. Moreover, many of these belts seem to be located at unexpected distances from their host stars. This challenges the conventional thinking that strongly correlated the distance of orbits with the temperature of the environment in which the bodies formed. Instead, these discoveries point to the possibility that materials can gather and persist in regions we didn't anticipate, suggesting that solar system formation can lead to a more varied and dynamic set of results than a one-size-fits-all model. Ultimately, the study of distant asteroid belts not only intrigues scientists, but also invites a deeper exploration into our own solar system's history. By comparing our solar system with others, we can gain new insights into the conditions that shaped our cosmic neighborhood. This ongoing research encourages us to consider the vast diversity of planetary systems throughout the universe, fundamentally reshaping our understanding of how these complex structures come into existence. The study of exoplanets in extreme environments, particularly those exhibiting tidal locking, has revealed fascinating insights into their potential habitability. Tidal locking occurs when a planet's rotation period matches its orbital period around a star, leading to one side of the planet perpetually facing the star while the other remains in unending darkness. This creates stark temperature differences between the two hemispheres. The sunlit side may become incredibly hot, while the dark side could descend into frigid temperatures. Researchers have found that these extreme conditions could still allow for the presence of liquid water, a vital ingredient for life as we know it. In the twilight zone, which lies between the hot and cold sides, temperatures might be more moderate. This region might provide a more stable environment where water can exist in liquid form, raising hopes that conditions here could support simple or even complex life forms. The possibilities in this zone make tidal-locked exoplanets intriguing candidates for further studies. Additionally, atmospheric conditions play a crucial role in the habitability of tidally locked planets. If an atmosphere is thick enough, it could help redistribute heat from the sunlit side to the dark side, effectively moderating temperature extremes. This means that, under the right circumstances, even extreme environments could sustain life, albeit potentially quite different from what we experience on Earth. Astrobiologists are continuously examining data from missions that focus on exoplanets, and they remain optimistic. The ongoing exploration of exoplanets in such unique circumstances deepens our understanding of life's adaptability. Each discovery makes us reconsider our definitions of habitability and opens new avenues for finding life beyond Earth in harsh and unexpected places. The discovery of potentially habitable moons in our solar system is a remarkable advancement that stretches our understanding of where life might exist beyond Earth. For many years, we have primarily focused on planets like Mars as possible hosts for life. However, recent explorations have revealed that moons such as Europa, Enceladus, and Titan present compelling environments that could support life, challenging our traditional views on habitability. Europa, one of Jupiter's largest moons, is covered by a thick layer of ice, beneath which there is strong evidence of a vast ocean of liquid water. This icy shell insulates the ocean, raising the potential for chemical reactions similar to those that might have occurred in the early Earth. Scientists are particularly intrigued by the idea that hydrothermal vents on the ocean floor could provide the necessary energy and nutrients to support life in such a dark and hostile environment. Similarly, Enceladus, a moon of Saturn, has been shown to shoot plumes of water vapor into space, which contain organic molecules. These findings suggest an energetic and complex environment beneath its icy crust. The presence of these building blocks of life hints at the possibility that microbial organisms could be thriving in these hidden oceans. This discovery pushes the boundaries of where we might find life, moving beyond the conventional realms we considered just a few decades ago. Lastly, Titan, also a moon of Saturn, presents a unique analogy to Earth with its rivers and lakes of liquid methane and ethane. While its surface conditions are vastly different from our own, The chemical processes occurring on Titan raise the tantalizing possibility of life forms that might utilize alternative biochemistries. These discoveries invite us to rethink our definitions of life and what conditions are truly necessary for it to thrive, expanding our search beyond Earth in ways we never imagined. The discovery of extremophiles on Earth has profoundly influenced our understanding of the potential for life beyond our planet. Extremophiles are remarkable organisms that thrive in conditions previously thought to be inhospitable, such as extreme heat, freezing temperatures, high radiation, and acidic environments. By studying these resilient life forms, scientists have begun to appreciate how life can adapt to the most unexpected circumstances. This adaptability raises tantalizing questions about the environments that might support life elsewhere in the universe. For instance, if organisms can survive in places like hydrothermal vents on the ocean floor, or in the harsh conditions of Antarctica's dry valleys, it leads us to consider similar extreme environments on other celestial bodies. Mars, with its frigid temperatures and radiation, and the icy moons of Jupiter and Saturn, such as Europa and Enceladus, might harbor conditions suitable for life, albeit in forms we have yet to imagine. Moreover, the discovery of extremophiles suggests that life could exist in environments that were previously dismissed as uninhabitable. This broadens the criteria for where we search for extraterrestrial life. It opens up possibilities in the atmospheres of distant planets and the subsurface oceans that may be hidden beneath thick ice layers. If life can thrive in these extreme conditions on Earth, why not elsewhere in the cosmos? Extremophiles serve as a testament to life's resilience and versatility. They remind us that life, in its myriad forms, is not just a delicate thread in a stable environment, but a robust force capable of surviving in the most extreme scenarios. The more we learn about these extraordinary organisms, the more we are compelled to explore the universe with hope and curiosity, always on the lookout for life's next extraordinary chapter. In recent years, astronomical advancements have allowed scientists to study the atmospheric composition of exoplanets, which are planets located outside our solar system. With powerful telescopes, researchers have been able to analyze the gases present in these distant worlds, leading to exciting implications regarding the potential for extraterrestrial life. Discoveries of elements and compounds that are typically associated with biological processes, such as methane and oxygen, have provided tantalizing hints that some exoplanets may have conditions suitable for life. One particularly significant finding involves the detection of substances like carbon dioxide and water vapor in the atmospheres of certain exoplanets. The presence of water is crucial, as it is a fundamental ingredient for life as we know it. Additionally, the combination of various gases not only suggests the possibility of an atmosphere conducive to sustaining life, but it also raises questions about the processes that could be creating these gases. For instance, while oxygen can result from biological activity, other explanations exist, making the search for life increasingly complex yet fascinating. The idea that exoplanets might host life has spurred a new field of astrobiology, focused on understanding how different environments could support living organisms. As we uncover more about these distant worlds, scientists are developing innovative ways to evaluate the potential habitability of exoplanets by studying their atmospheres. This includes launching missions designed to analyze the light that filters through a planet's atmosphere, thus revealing its chemical makeup. Each new discovery adds a piece to the puzzle of what constitutes a habitable environment. Ultimately, as researchers piece together the atmospheric profiles of exoplanets, they are proclaiming a shared curiosity about the universe's potential inhabitants. Each new finding invites more questions about whether we are alone or if life exists elsewhere among the stars, igniting a sense of wonder and exploration that drives the ongoing search for extraterrestrial life. The cosmos may hold more surprises than we can currently imagine, and the study of exoplanet atmospheres is just one promising avenue toward uncovering those mysteries. As we gaze into the vast expanse of the cosmos, humanity has cast a curious ear towards the heavens, listening for signals that might hint at intelligent life beyond our planet. Among the most fascinating occurrences are the so-called WOW signal, received in 1977. Astronomer Jerry R. Ehman detected this powerful burst of radio waves while working on a SETI project at Ohio State University. The intensity and narrowband nature of the signal suggested it could be artificial in origin, though it has never been replicated or identified since. This single 11-minute signal sparked the imaginations of many and raised tantalizing questions about the possibility of extraterrestrial civilizations. Another intriguing signal is known as the fast radio bursts, or FRBs. These brief, intense bursts of radio emissions last just milliseconds, yet they release immense energy, equivalent to the power output of the sun over several days. The origin of these bursts remains mysterious, with some theories proposing they stem from neutron stars, while others suggest they may be the product of extraterrestrial technology. Each new observation pushes our understanding of the universe, challenging our assumptions and heightening our sense of wonder about what else might be out there. In addition to these signals, a host of other enigmatic phenomena catches the attention of scientists. For instance, the repeating signals from FRBs have sparked debates over whether they could be signals from advanced civilizations. The Drake equation, a formula used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way, further adds another layer to this exploration. While we may yet be limited in our knowledge, the quest to uncover signs of intelligent life fuels not just scientific endeavors, but also our collective imagination. Ultimately, these perplexing signals serve as a reminder of our place in the universe. Each discovery leads to new questions, urging humanity to continue looking up at the stars, driven by the hope that we might one day discover that we are not alone. The signals we have received, though they remain enigmatic, illuminate the passionate pursuit of knowledge that lies at the heart of our existence. The discovery of microbial fossils on Mars has profoundly reshaped our understanding of the planet's history and its potential for harboring life. For years, scientists have speculated about whether Mars could have supported life. The presence of these fossils suggests that microbial organisms could indeed have thrived in certain environments on the planet, primarily when conditions were more hospitable. This indicates a warmer and wetter past, where liquid water was likely present on the surface. These findings provide crucial insights into the ancient Martian environment. It reinforces the idea that Mars once had the essential conditions for life as we know it. Our understanding now includes the possibility that large bodies of water might have existed, alongside various geological processes that could have sustained microbial life forms over millions of years. This reshapes the narrative from Mars being a cold, barren desert to a planet with a dynamic, possibly life-supporting climate in its early history. Moreover, the existence of microbial fossils encourages comparisons with Earth's own early life forms. It raises intriguing questions about how life might have started on different planets under similar conditions. This comparability shines a light on the adaptability of life and how it might arise in diverse environments across the universe. When we delve into astrobiology, these findings serve as a cornerstone for understanding life's resilience and the potential for life beyond Earth. The presence of microbial fossils on Mars not only broadens our perspective of its geological past, but also invites us to reconsider the possibility that we are not alone in the universe. It prompts further exploration of both Mars and other celestial bodies, as we seek answers to fundamental questions about our existence and the very nature of life itself. the journey to understand Mars is far from over, with tantalizing clues still waiting to be uncovered. As scientists continue to explore the cosmos, searching for signs of life beyond Earth, they've developed innovative methods to detect biosignatures on distant planets. One of the most significant advancements involves the use of space telescopes, equipped with precise instruments designed to analyze the atmospheres of exoplanets. These telescopes can detect certain gases, such as oxygen and methane, which, when found together in significant quantities, may suggest biological activity. Spectroscopy is at the heart of this process. It works by breaking down light emitted or absorbed by a planet's atmosphere into its component colors. By studying the specific wavelengths that are absorbed by various molecules, scientists can identify the presence of potential biosignatures. For instance, the signature of chlorophyll, which is used by plants on Earth, can indicate the presence of photosynthetic life elsewhere in the universe. Another exciting method involves the use of transit photometry. When a planet passes in front of its host star, it causes a temporary dimming of that star's light. By measuring these slight changes in brightness, scientists can infer information about the planet's size, composition, and atmosphere. This technique has been pivotal in locating Earth-sized planets in the habitable zones of their stars, making them prime candidates for detailed study. Moreover, advancements in computer modeling and artificial intelligence are being harnessed to process vast amounts of data from these observations. This enables researchers to distinguish between potential biosignatures and false positives caused by non-biological processes. With each step forward, the dream of understanding whether we are alone in the universe becomes more tangible, sparking wonder and curiosity about the mysteries still waiting to be uncovered. The study of cosmic radiation exposure has opened up fascinating avenues for understanding the origins and evolution of early life forms on Earth. Cosmic radiation, which consists of high-energy particles from outer space, bombards our planet constantly. This radiation can penetrate the atmosphere and reach the surface, potentially impacting living organisms. As scientists have investigated its effects, they have uncovered insights into how early life might have adapted to these environmental challenges. One key area of research focuses on the role of cosmic radiation in the formation of organic molecules. When high-energy particles collide with atmospheric elements, they can trigger complex chemical reactions, producing a variety of organic compounds. These compounds are essential building blocks of life. Thus, cosmic radiation may have contributed to the primordial soup from which life emerged billions of years ago, suggesting that our cosmic environment played a significant role in shaping our biochemical origins. Moreover, studies of radiation exposure have led to insights into how early life forms might have developed resistance mechanisms. For instance, some microorganisms today exhibit remarkable resilience to high levels of radiation. This resilience could serve as a clue to how life on Earth adapted to the harsh conditions of its early environment, where radiation levels were likely quite different from what we experience now. Understanding these adaptations helps scientists piece together the narrative of life's evolution. Finally, the implications extend beyond Earth. If cosmic radiation was a factor in the evolution of life here, similar processes could potentially occur on other planets or moons with atmospheres exposed to space. This encourages astrobiologists to re-evaluate the conditions necessary for life, reinforcing the idea that the cosmos may be more interconnected with life's origins than we initially believed. As research continues, the story of cosmic radiation and life's beginnings only becomes more compelling and complex. Traditionally, we picture galaxies as isolated islands in the vast cosmic sea, each spinning in its own space. However, recent observations have unveiled surprising relationships that paint a different picture. revealing a more interconnected universe than we once thought. Astronomers have found instances where galaxies are not only close neighbors, but are actively interacting, often in dramatic ways. One striking example of these connections can be seen in galaxy pairs or groups. When two galaxies come near each other, their gravitational forces can lead to fascinating distortions. Sometimes they begin to merge, creating a new, larger galaxy altogether. In other cases, one galaxy can strip material from another, leading to the formation of new stars. This galactic affection is common, and it challenges the notion that galaxies evolve in isolation. Instead, these interactions suggest a dynamic cosmos teeming with relationships. Additionally, surveys have uncovered extensive galaxy filaments. These monumental structures are part of what is known as the cosmic web, which connects groups of galaxies like threads in a grand tapestry. Through this web, material and energy can be exchanged over vast distances, facilitating interactions between seemingly distant galaxies. Understanding these connections helps astronomers explain phenomena like dark matter and the large-scale distribution of galaxies across the universe. Such discoveries compel us to reconsider how we understand the universe. Rather than viewing galaxies as separate entities floating alone in the cosmos, we now see them as participants in a grand cosmic dance. This interconnectedness not only enriches our understanding of galaxy formation and evolution, but also stirs wonder about the fabric of our universe, reminding us that even in the vastness of space, nothing exists in complete isolation. Recent findings about the interactions between dark matter and ordinary matter have provided vital insights that are reshaping our understanding of the universe. Historically, dark matter has been viewed as an elusive substance that does not interact with ordinary matter except through gravity. However, new observations suggest that there may be more complex interactions at play. These findings impact how cosmologists model the formation and evolution of structures within the universe, such as galaxies and galaxy clusters. One significant development in this area is the growing evidence that dark matter particles might interact with each other or with normal matter beyond just gravitational forces. These interactions could influence how galaxies form and evolve. For instance, if dark matter can clump together more efficiently due to these additional interactions, it could lead to faster galaxy formation than previously thought. This means that our models must account for a more dynamic interplay between dark matter and the visible universe. Moreover, the way we think about the distribution of dark matter within galaxies has also shifted. Traditional models assumed a smooth and uniform distribution. However, recent simulations and observations suggest that dark matter may create more complex structures. This revelation prompts scientists to refine their models to better align predictions with observational data, such as the clustering of galaxies and the cosmic microwave background radiation. These advancements push the boundaries of our understanding, provoking new questions about the fundamental composition of the universe. With each finding, we inch closer to a comprehensive model that accounts for not only what we can see, but also the vast unseen forces at play. By continuing to study these interactions, we hope to unlock the secrets of dark matter, ultimately deepening our grasp of cosmic evolution and our place in the universe. The relationship between the solar cycle and climate change on Earth is a field of study that has fascinated scientists for years. The solar cycle refers to the approximately 11-year cycle of solar activity, which includes variations in sunspots, solar flares, and other phenomena that reflect the sun's magnetic activity. This cycle does influence Earth's climate, albeit in subtle ways. Research has indicated that increased solar activity generally leads to a slight rise in Earth's temperatures. This happens because a more active sun emits more energy, which can affect weather patterns and atmospheric conditions. Studies utilizing satellite data have shown a correlation between periods of high solar activity and warmer global temperatures, suggesting that while the sun plays a role, its impact is not as significant as other factors, such as greenhouse gas emissions from human activity. One fascinating groundbreaking study published in recent years analyzed how solar activity interacts with the Earth's atmosphere. Scientists discovered that increased solar radiation could enhance certain atmospheric conditions, leading to changes in climate. For instance, during solar maximum, when sunspots peak, there is a corresponding uptick in energy reaching Earth's surface. However, this effect is relatively small compared to the dramatic shifts caused by human-induced climate change. Ultimately, while the solar cycle does influence climate, it operates in a much larger context of various contributors, including volcanic eruptions, ocean currents, and human activities. The consensus among scientists today is that while we should never discount the sun's influence, the current trends in climate change are predominantly driven by human actions. This understanding encourages us to continue exploring our solar system while remaining vigilant about our planet's health and stability. Star formation occurs in a variety of environments throughout the universe, and the differences in these regions have significantly shaped our understanding of galactic evolution. In dense areas like the centers of galaxies, stars tend to form in larger clusters and often develop much more quickly. This rapid formation process leads to an abundance of massive stars that burn brightly for a brief period before exploding as supernovae. These events not only enrich the surrounding medium with heavy elements, but also influence how other stars and planets form, providing critical insights into the life cycle of galaxies. In contrast, in more diffuse regions of a galaxy, star formation is generally slower and less intense. These areas may produce stars over millions or even billions of years. The stars that form in these environments are often smaller and less luminous. By studying these diverse stellar populations, astronomers have gained valuable knowledge about how different conditions affect the rate and type of star formation, and consequently, the overall development and structure of galaxies over time. One fascinating aspect of this dynamic picture is how interactions between galaxies can spur new star formation. For instance, when two galaxies collide, the gravitational forces at play can compress gas and dust, triggering a wave of star birth that might not have occurred in isolation. This phenomenon underscores the importance of environmental factors and galactic interactions in shaping the evolutionary paths of galaxies and the stars within them. As we continue to explore the universe, advanced observational techniques reveal even more about the conditions conducive to star formation. These insights challenge previous assumptions about galaxy growth and highlight the complex interplay between different regions of space. Each discovery propels us further into a deeper understanding of galactic evolution, showing that the universe's narrative is continuously being rewritten with each new find. Dramatically shifting our understanding of the universe. In the early days of astronomy, simple refracting telescopes allowed stargazers to glimpse the wonders of the night sky, but were limited in their capacity to collect light. This meant that many distant celestial objects remained shrouded in mystery. However, as technology advanced, astronomers began to build larger, more powerful instruments that could capture fainter light from deeper in space. One of the most significant advancements has been the development of reflecting telescopes, which use mirrors instead of lenses. This innovation allows for larger structures that can gather more light without the distortion caused by glass lenses. Telescopes like the Hubble Space Telescope, launched into orbit in 1990, took this concept to the next level, providing crystal-clear images free from the interference of Earth's atmosphere. Hubble's stunning images have revealed the grandeur of distant galaxies, nebulae, and the intricate details of cosmic phenomena, changing our perspective on the universe. Moreover, the technological leap into radio and infrared telescopes opened entirely new windows to the cosmos. These telescopes can detect wavelengths of light invisible to the human eye, offering insights into the early universe and allowing scientists to study cool, dim celestial bodies like brown dwarfs and distant planets. Ground-based instruments like the Very Large Array and space observatories like the James Webb Space Telescope have further pushed our boundaries, enabling discoveries about the formation of stars, the composition of exoplanetary atmospheres, and the very early stages of cosmic evolution. As each new telescope comes online, our universe continues to reveal its secrets. The ability to peer deeper into space not only expands our knowledge, but also fuels the imagination, inspiring generations to ponder our place in this vast cosmos. With each stunning discovery, we are reminded of just how much there is left to explore and how crucial advancements in telescope technology are to unlocking the mysteries of the universe. Space probes serve as our eyes and ears beyond the confines of Earth, allowing us to explore distant celestial bodies and cosmic phenomena in ways that telescopes cannot. Unlike telescopes that rely on gathering light and other forms of radiation from afar, space probes travel directly to the locations of interest. By getting closer to planetary systems, moons, and comets, these robotic explorers can collect data firsthand and deliver it back to scientists here on Earth. These missions are designed with specific scientific objectives in mind. For example, some probes study the atmosphere and surface conditions of other planets, while others might analyze the composition of asteroid belts or the magnetic fields surrounding distant worlds. Their onboard instruments can measure temperature, radiation levels, geological formations, and even search for signs of life, enhancing our knowledge about the building blocks of the universe and the potential for life beyond our planet. One of the most remarkable aspects of space probes is their ability to transmit data from extreme environments that would be impossible for humans to safely visit. Consider the Voyager spacecraft, launched in the 70s, which are now more than 40 years old and still sending valuable information about interstellar space. Missions like the Mars rovers have allowed us to explore our neighboring planet in detail, revealing a complex history of water and geology, paving the way for future human exploration. As we push the boundaries of our cosmic knowledge, space probes highlight not only our curiosity, but also our resilience. They embody our quest to understand fundamental questions about the universe, such as the creation of planetary systems and the potential for life elsewhere. Each mission deepens our connection to the cosmos, unfurling the mysteries of the universe bit by bit, one probe at a time. The integration of artificial intelligence in astrophysical research has profoundly altered how scientists analyze cosmic data. Traditionally, astronomers faced the daunting task of sifting through massive amounts of information gathered from telescopes and satellites. With the universe presenting an unfathomable array of data, from the faintest star signals to the intricate patterns of galaxies, human analysis alone often proved insufficient. Enter AI, with its remarkable ability to recognize patterns, sort through data, and draw conclusions much faster than any human could. One of the most significant contributions of AI is its ability to identify celestial phenomena that might otherwise go unnoticed. For instance, machine learning algorithms are now employed to detect exoplanets by analyzing the dimming of stars. When a planet passes in front of its star, even momentarily, it causes a measurable dip in brightness. AI systems can analyze light curves, spotting these tiny variations even amidst noise that would baffle human observers. This has led to the discovery of numerous exoplanets, expanding our understanding of potential worlds beyond our own. Moreover, AI is revolutionizing the detection of gravitational waves, ripples in space-time caused by massive cosmic events like black hole collisions. The immense volume of data generated by detectors such as LIGO can overwhelm conventional methods. AI algorithms can quickly process this data stream, flagging potential gravitational wave events with greater accuracy and speed. As a result, researchers can respond rapidly to significant findings, coordinating with observatories to observe these phenomena across multiple wavelengths. As researchers push the boundaries of astrophysical knowledge, AI continues to pave new avenues for exploration. Its application is only expected to grow as scientists develop more sophisticated algorithms and machine learning models. With this partnership between humans and machines, we stand on the brink of exciting discoveries that may redefine our understanding of the universe, making the stars more accessible than ever before. The outer planets of our solar system have always held a certain allure, shrouded in mystery and grandeur. In recent years, missions like NASA's Juno spacecraft and the European Space Agency's Jupiter Icy Moons Explorer have provided us with a treasure trove of new insights into these distant giants. Juno, for instance, has revealed that Jupiter, the largest planet in our solar system, boasts an intricate and complex magnetic field, far more powerful and chaotic than we previously understood. This newfound knowledge helps us appreciate the planet's dynamic environment and its role in the solar system. One of the most fascinating discoveries from these missions involves understanding the weather systems on these planets, especially Jupiter. Juno has captured stunning images of Jupiter's swirling storms, including the iconic Great Red Spot, a storm that has raged for centuries. The data gleaned from Juno indicates that these storms extend deep into the planet's atmosphere, far below the cloud tops. This insight has sparked new questions about the thermal dynamics of gas giants and how such immense storms maintain their energy over long periods. Furthermore, our explorations are not limited to Jupiter. The study of Saturn's moon Enceladus, through missions like Cassini, has uncovered subsurface oceans that may harbor conditions suitable for life. The geysers that erupt from Enceladus's south pole, spewing water vapor and organic materials into space, suggest that there could be hydrothermal activity on the sea floor beneath its icy crust. These findings have propelled Enceladus to the forefront of astrobiological research, giving scientists a reason to consider the moon as a potential home for microorganisms. These missions collectively enhance our understanding of planetary formation and evolution, not just within our solar system, but also in the broader universe. With each layer of discovery, we not only unravel the characteristics of these far-off worlds, but we also deepen our appreciation for the intricate mechanics of our own cosmic neighborhood. The ongoing research promises to continue sparking curiosity, driving future missions, and inspiring the next generation of explorers. In recent years, advancements in imaging technologies have revolutionized our ability to explore the cosmos. Techniques that once felt like science fiction are now at the forefront of astronomical research. One significant development is the use of high-resolution telescopes equipped with adaptive optics. This technology allows astronomers to correct for the distortions caused by our atmosphere, resulting in images that reveal intricate details of celestial objects that were previously obscured. Another remarkable advancement is the emergence of space-based observatories, like the Hubble Space Telescope and the James Webb Space Telescope. These instruments operate beyond Earth's atmosphere, providing clearer images by avoiding atmospheric interference entirely. The James Webb Space Telescope, in particular, specializes in capturing infrared light, which means it can see through dust clouds that often shroud stars and planetary systems. This capability enables scientists to detect stars in the early stages of formation and to observe distant galaxies as they were billions of years ago. Moreover, radio imaging technologies have transformed our understanding of phenomena like black holes. Radio telescopes, such as the Event Horizon Telescope, work in a completely different part of the electromagnetic spectrum. This network of telescopes provided us with the first ever image of a black hole's shadow, a feat that unveiled the mysterious region surrounding these enigmatic cosmic giants. Such images offer crucial insights into the behavior of matter and energy at the edges of black holes. Beyond these tools, advancements in computer algorithms and machine learning are also playing a vital role. These technologies analyze vast amounts of data, identifying patterns and anomalies that might escape the human eye. As a result, we are unveiling secrets of the universe that have long been hidden, and each new discovery invites us to ponder even greater questions about the nature of existence and our place among the stars. Profound challenges for scientists, especially when explored through the lens of astrophysics. Time is not merely a ticking clock, it is a dimension that is interwoven with the fabric of space itself. One fundamental challenge arises from the relativity of time, a concept introduced by Albert Einstein over a century ago. According to his theories, time is not a uniform progression for everyone. It can stretch and compress depending on gravitational fields and relative speeds. This makes seeking a definitive understanding of time particularly complex. Another significant hurdle is the measurement of time across vast cosmological distances. In our universe, events happen over such enormous scales that timing them accurately becomes a daunting task. For instance, we may observe a star exploding in a supernova, but because that light has traveled millions of years to reach us, we must take great care in interpreting the timing of that event. Scientists often rely on light as a universal clock, but the variations in light behavior and its interaction with different cosmic materials introduce uncertainties. Moreover, when we observe celestial bodies moving through space, we are confronted with the phenomenon known as time dilation. For example, an astronaut traveling close to the speed of light would experience time differently than someone on Earth. This discrepancy highlights the relative nature of time and complicates our ability to talk about a universal timeline for the cosmos. Finally, the very nature of time itself is still a subject of intense debate among scientists. Questions arise: is time a fundamental part of the universe, or is it an emergent property that arises from other phenomena? These unresolved questions contribute to the ongoing mystery of time in astrophysical research. As our understanding of the universe evolves, so too will our grasp of time, transforming it from a simple measure into a rich tapestry of cosmic history and existence. Groundbreaking experiments conducted right here on Earth have significantly deepened our understanding of how matter behaves under extreme cosmic conditions. Scientists have turned to particle accelerators like the Large Hadron Collider, where they smash particles together at incredible speeds. These collisions recreate conditions akin to those found just moments after the Big Bang. By observing the outcomes, researchers glean invaluable insights into the fundamental forces and particles that shape our universe. Additionally, experiments in extreme temperature and pressure environments, like those found deep within stars or during supernova explosions, have been realized in laboratories. For example, by squeezing tiny samples of matter with powerful lasers, scientists simulate the high-energy conditions that occur in stellar cores. This helps us comprehend phenomena such as nuclear fusion, which is essential for the generation of energy in stars, and by extension, for the creation of the elements that make up our universe. Another fascinating area of research involves understanding the behavior of materials in incredibly strong magnetic fields, similar to those around neutron stars. These ultra-dense celestial objects exert gravitational forces so intense that a mere sugar cube-sized amount of their material would weigh as much as a mountain on Earth. Through laboratory experiments involving high magnetic fields and low temperatures, Scientists examine how matter behaves in these conditions, providing clues about the mysterious properties of neutron star cores. Moreover, the study of cosmic rays, high-energy particles from outer space, allows researchers to investigate matter's reactions when bombarded with energy levels far beyond anything experienced on Earth. Each of these experimental endeavors not only shines a light on the workings of matter in extreme environments, but also enriches our understanding of the cosmos itself, bridging the gap between our planet and the vast universe around us. Time asymmetry is a fascinating concept that speaks to the very nature of our universe. At its core, this phenomenon refers to the observation that time seems to flow in one direction, from the past to the future. While we can recall memories and witness events that have occurred, we cannot directly reverse them. This observation leads us to consider the implications of time's arrow for the overall structure of the universe. One of the most telling indicators of time asymmetry is the second law of thermodynamics, which states that in an isolated system, the level of disorder, or entropy, tends to increase over time. Imagine a glass of ice water. As time passes, the ice melts, and the system becomes more mixed until it reaches a state of equilibrium. This tendency toward greater disorder suggests that our universe has a preferred direction, leading us to conclude that time flows forward. The increase in entropy hints at the initial low-entropy state of the universe right after the Big Bang. Understanding this interplay between time and thermodynamics also raises curious questions about the structure and fate of the universe. If time asymmetry implies a distinct beginning, it suggests that the universe was once in a state of extreme order and density. As the universe expands and evolves, it transitions into states of greater entropy, which shapes its large-scale structure. The clumping of matter into galaxies and stars represents one manner in which this transition manifests. Ultimately, time asymmetry may reveal that the fabric of the universe is more intricate than we can fully grasp. This linear progression of time hints at untold mysteries regarding causality, time travel, and the future of cosmic evolution. As we explore these questions, we find ourselves in a realm where physics and philosophy intertwine, inviting continuous wonder about the nature of existence itself. Cosmic inflation is a theory that proposes a rapid expansion of the universe during its earliest moments, just after the Big Bang. This concept not only explains the uniformity we observe in the cosmos, but also influences our understanding of the universe's ultimate destiny. As scientists delve deeper into the implications of inflation, they uncover insights that shape our views on what lies ahead for the universe. One significant impact of inflationary theory is its relation to the universe's expansion. Observations show that the universe is not only expanding, but that this expansion is accelerating. This led to the introduction of dark energy, a mysterious force that seems to push galaxies apart. The inflationary model predicts that this expansion could continue indefinitely, suggesting that the universe might stretch infinitely into the future. In this scenario, galaxies would drift further apart until they become isolated, leading to a cold and dark cosmos. Contrastingly, some variations of inflationary theory propose the possibility of a cyclical universe. This view speculates that our universe could undergo phases of expansion and contraction. In each cycle, the universe might face a rebirth where conditions are reset. This idea provides a fascinating perspective on cosmic evolution, hinting at a universe that is not only dynamic but potentially eternal, with periods of regeneration. Discoveries related to cosmic inflation refine our understanding of the universe's fate. They challenge us to consider various scenarios, from endless expansion to cyclic rebirth. As researchers continue to explore these ideas, they bring us closer to unraveling the profound mysteries of the universe, providing a window into its past while speculating on its future trajectory. Each new insight serves to remind us of the vastness of cosmos and our place within its unfolding narrative. The study of black hole thermodynamics has sparked a fascinating shift in our understanding of time and space. Traditionally, time and space were viewed as static backdrops where events occur. However, the intricate properties of black holes introduce a dynamic interplay between these dimensions, fundamentally altering how we perceive them. Black holes, once seen merely as cosmic drains, now play a pivotal role in unraveling deeper truths about the universe. One of the most intriguing aspects of black hole thermodynamics is the connection between entropy and information. It was proposed that black holes have entropy, a measure of disorder or missing information. This revelation implies that the information about everything that falls into a black hole is not lost, but rather encoded on its surface or event horizon. This idea has led scientists to reconsider the nature of reality itself, suggesting that our three-dimensional universe might be an emergent phenomenon rooted in a more complex two-dimensional realm of data. Additionally, the concept of space-time has also evolved. In the realm of black holes, space-time is seen as more fluid and malleable than previously thought. The event horizon marks a boundary beyond which we cannot see, hinting that reality behaves differently under extreme gravitational conditions. This perspective encourages scientists to theorize that space-time itself may be woven from the same informational fabric that defines black hole information. These novel models of time and space challenge our classical intuitions. They invite us to ponder. Can we truly know the limits of the universe if information can persist even in the deepest parts of black holes? As research progresses, we stand on the brink of redefining our understanding of the cosmos, with black holes serving as both cosmic enigmas and keys to unlocking the ultimate nature of reality itself. Cosmic dust, often overlooked, plays a vital role in understanding the universe's history and formation. These tiny particles, mainly composed of carbon, silicon, and metals, are not merely nuisances in observational astronomy. They are essential clues to the processes that shape galaxies, stars, and even planets. Strikingly, cosmic dust is believed to contribute to the very building blocks of life, emphasizing its importance in the cosmic narrative. Recent discoveries indicate that this dust is formed in the violent environments of space, such as the aftermath of supernova explosions. When massive stars exhaust their nuclear fuel, they explode, scattering stardust across the cosmos. This dust is not just debris. It provides insights into the elemental composition of the universe and how these elements aggregate to form new celestial bodies. For instance, studies of cosmic dust revealed that it serves as a catalyst for the formation of complex molecules, which are foundational to the chemistry of life as we know it. Moreover, cosmic dust has been observed in the most distant and ancient galaxies, giving astronomers a window into the early universe. By analyzing dust at these vast distances, scientists can piece together the timeline of star formation and galactic evolution. It appears that dust not only shelters and nurtures young stars, but also influences their growth and development. This interconnectedness underscores the idea that dust is fundamental to the life cycle of galaxies, acting as a bridge between the old and the new. Additionally, the study of cosmic dust has significance beyond star formation. It can help shed light on the evolution of planetary systems as dust particles collide and stick together, forming larger objects, including asteroids and comets. Through this lens, cosmic dust is not just a byproduct, it is a dynamic participant in the cosmic processes. The ongoing exploration of cosmic dust continues to reveal its multifaceted role, reminding us that the smallest particles can have the most profound impacts on the universe. The International Space Station, or ISS, serves as a remarkable laboratory for studying the effects of prolonged space travel on humans and our technology. Since its launch, astronauts have lived and worked aboard the station for extended periods, providing invaluable insights into how our bodies react to microgravity and radiation. These experiences help us understand physical changes such as muscle atrophy, bone density loss, and alterations in vision. Observing these effects has been essential in preparing for longer missions, such as a journey to Mars, which may last several years. One key lesson learned from the ISS is the importance of physical fitness. Crew members on the station must exercise daily to counteract muscle and bone deterioration. This realization has led to the development of exercise regimens that can be implemented on long-duration flights. The need for physical activity, combined with a healthy diet, emphasizes that maintaining human health should be a focal point of future deep space missions. Psychological well-being also emerges as a critical factor. The isolated and confined environment of the ISS can affect astronauts emotionally. With a team living in close quarters for extended times, researchers have delved into the dynamics of crew interactions and coping strategies. Developing effective communication and support systems is becoming essential as we envision future missions far from Earth's comforting embrace. Additionally, the ISS has tested life support systems, including water recycling and air purification technology. These innovations are vital for sustainability on long missions, where resupplying from Earth is impractical. Thus, the ISS is not just a platform for exploration, it is also a cornerstone in our quest to make long-term space travel viable for humanity. The lessons learned here will undoubtedly shape our interplanetary ambitions. Recent findings about the solar wind have brought fascinating insights into how this stream of charged particles from the Sun impacts Earth's atmosphere. The solar wind plays a critical role in shaping space weather and can have significant implications for our planet. Indeed, it influences not just the atmosphere, but also our technology and climate patterns. The solar wind can lead to disturbances in Earth's magnetic field, creating phenomena such as auroras, those stunning natural light displays found near the polar regions. When these particles collide with gases in our atmosphere, they excite those gases, resulting in bright colors dancing across the night sky. However, this interaction isn't purely beautiful, it also poses risks. Strong solar storms can disrupt satellite operations, interfere with GPS systems, and even overheat power grids on Earth. More recent research indicates that the solar wind may also affect Earth's climate over longer timescales. While the links remain complex and are still being unraveled, scientists suggest that variations in solar activity could modulate cloud cover through cosmic rays, which are influenced by the solar wind. This could potentially affect regional weather patterns and long-term climate stability. Understanding these interactions not only helps us appreciate the delicate balance of forces at play in our solar system, but also emphasizes the importance of monitoring solar activity. As we continue to explore these relationships, we gain valuable insights that could help us prepare for potential impacts, ensuring our technology and safety remain intact in the face of the captivating yet powerful forces of the cosmos. Human exploration in space has profoundly enhanced our understanding of life beyond Earth. By venturing into the cosmos, we not only learn about our own planet's conditions, but also gather crucial insights into what makes environments habitable. Through missions to other celestial bodies, we analyze their atmospheres, surfaces, and potential resources, allowing us to identify which places in the universe might support life, even if it is vastly different from our own biological makeup. One of the most striking outcomes of human space exploration is the discovery of extremophiles on Earth, organisms that thrive in conditions previously thought to be uninhabitable. These discoveries suggest that life could exist in unexpected environments elsewhere in the universe, such as the icy moons of Jupiter or Saturn. By testing life's resilience and adaptability here on Earth, we can draw parallels to what we might find in our solar system and beyond. Furthermore, human missions, like those to Mars and the ongoing investigations of the International Space Station, enable scientists to conduct experiments in microgravity. This unique environment allows us to observe biological processes in ways that are simply not possible on Earth. Such studies not only help us understand how life functions in space, but also provide clues about how life could originate and develop on other planets. As we send more astronauts into space and continue to explore with rovers and sophisticated instrumentation, our understanding of life's possibilities expands endlessly. Each mission adds a new piece to the puzzle of whether we are alone in the universe, fueling our curiosity and ambition to explore further, pushing the boundaries of our knowledge into the vast unknown. Cosmic rays, the high-energy particles originating from outer space, have intrigued scientists and researchers for decades. Their effects on biological organisms uncover a remarkable tapestry of surprising truths. For example, studies have shown that these particles can cause mutations in the DNA of living organisms. When these cosmic rays collide with atoms in our atmosphere, or even within the cellular structure of plants and animals, they can produce secondary radiation that produces free radicals. These free radicals can disrupt genetic material and influence evolutionary processes over time.